Alright, welcome back to the part 2 for this video. We're just going to cover a few more examples for simple proofs. The last video was getting a little bit long, so we'll just do it in this video. So, another simple proof example, and I'll just make sure my pencil is a different color. Okay, so example number 4. Let's say for all integers x, there exists an a such that 2x squared minus ax equals 0. And then if we need to write a proof for that, you might want to pause the video, try writing it out yourself. Okay, welcome back. So, let x be an integer such that x is a real number. Right, so again, this is always going to be the start to your proofs. Now, how do you want to go about proving this? Well, there exists an integer a, so obviously we just need to find one integer in the entire universe that proves this premise, and we have accomplished the proof. Right, that's how there exists proofs work. So, I found the integer. If we have x as the integer, and then our a, pick a to be 2x. So a equals 2x. Now line 3, therefore 2x squared minus ax equals 2x squared minus 2x squared equals 0. Thus, this premise is true. End proof. Now, here's the thing. This proof was really easy because all you had to do was isolate for a in order to find that one a value that satisfied this equation. Right? Very self-explanatory. But in all proofs, it might not be that self-explanatory, especially in proof by induction, which we'll get to, obviously, as I said. But yeah, that's pretty much the case. Again, just think creatively when you're looking for these proofs. For example, there might be more complex theorems that you may have to prove. So we'll go over one of those examples as well. Example number 5, which states, for all integers k, if k is odd, then k squared plus 2 is prime. So how do we prove an example like this? Well, this is a for all case, and in this one the question told me that I forgot to mention that this is false. Alright, so this is information that I have. Okay, so how do I prove a for all quantifier to be false? Well, I just find one counterexample. So again, that's not too difficult, but how do we find the counterexample? In this example, is really easy. We just isolate for a. But in this example, it's going to be a little bit tricky, right? If you're obviously a high school or university student, it's not going to be that tricky. You may have already solved it, but not as self-explanatory as the last one. So, this theorem is false, and we can prove it using a counterexample. Proof by counterexample. So, we pick k equals 5, right? Or pick k equals 5. I forgot to mention pick k equals 5. 2. Then k is an odd integer. Three, further, if k squared plus 2 equals 5 squared plus 2 equals 27, then that also equals 3 times 9, making it not prime, right? Thus, k squared plus 2 is not prime. Now this was very easy how do I come up with k equals 5? This is very easy, right? You just go through all the odd numbers. What are the odd numbers? 1, odd integers, 1, 3, 5. 1 and 5 in this situation would be prime, or 1 and 3 would be prime. 5 is not prime, so 5 is our counterexample, and we're done, right? Is not prime, and then we can end proof. So again, very simple proof. Now, we can also get into recursive, or not recursive, but like partially recursive cases. So one sec, let me just pull up the example. Okay, there we go. So, sorry about that. Example number 6. Now this is not exactly a proof by recursion. I'll switch again marker color so you guys can see. This is not exactly a proof by recursion, but it's pretty close to it. So, the theorem is for all integers n is greater than or equal to 0, 2 divides n times n plus 1 evenly. Now for the proof, let n be an integer such that n is greater than or equal to 0. And this should have been line 1. Alright, my apologies. So that should have been line 1. Again, just pick n to be an integer. We didn't do that for this one, or we kind of did. We picked k equals 5. But, for this one, we just picked it to be an arbitrary integer because we don't know yet, right? Why don't we know it yet? Because this theorem is actually true, right? Now, even if the question doesn't tell you if a theorem is true or false, you kind of have to figure it out. Like, you kind of have to go through the proof in your mind without writing it out. If you can find a counterexample, that's perfect. It's false. But if you can't find a counterexample for many examples, or you can't find a way to exempt the premise of the proof, then you've basically stumbled upon a proof that is that cannot be proven false. In other words, the for all proof would be true. So this one is true. If you run through the scenario in your head, you'll figure out why it's true. And we just prove it using the same logic. So let n be an integer such that n is greater than or equal to 0. Again, we can split this up into cases. Case 1, if n is odd, right? So we prove it for odd cases and then even cases. That's one way to prove for all. Another way was up here. We proved it for all numbers less than or equal to 3, and then for all numbers greater than or equal to 4. So you can do case-by-case proofs like that for large proofs like this. So case 1, if n is odd, then n equals 2k plus 1 for some int k, right? So obviously 2k is an even number, 2k plus 1 is an odd number. So obviously that is a statement that is true. 3. So n plus 1 equals 2k plus 1 plus 1 equals 2k plus 1, and n plus 1 equals 2n k plus 1. 4. So it's divisible by 2, right? Because we can divide this by 2 evenly without a remainder or a decimal, right? So it's divisible by 2. Now case number 2, this is pretty self-explanatory. If n is even, then n equals 2k, which is obviously divisible, right? So easy to prove. And then thus this theorem is true. So again, these 6 examples are very basic level problems. These 6 examples were very basic level problems, just to give you an insight into how formal proofs are written. If you have obviously examples in an assignment or an exam, they're going to be much more difficult. And we will cover those types of examples in future videos throughout this course. So thank you so much for watching again, and if you found this video useful, please like and subscribe.